Millions of manufactured products, perfectly engineered and expensively transported, eventually end up in a hole in the ground. This physical waste exposes the core flaw of the traditional linear economy. We make, we use, and we immediately dispose. The economic and philosophical answer to this systemic waste is the circular economy, the concept that materials should circulate continuously rather than ending their life cycle in a landfill. But a philosophy doesn't run a warehouse. Without a concrete system to actually retrieve, transport, and process those discarded goods, the circular economy remains an abstract theory. To make it functional, businesses must implement a specific operational framework, the closed-loop supply chain. A traditional linear supply chain extracts resources, builds a product, and walks away after the point of sale. A closed-loop system is intentionally designed to capture whatever residual value remains in that product after the customer is done with it. Moving to this model addresses environmental necessity, but it also forces a complete redesign of how an industry extracts economic value from its own end-of-life materials. The primary reason companies adopt this architecture is simple economics. It allows operators to extract untapped financial value from customer returns while significantly lowering their raw material procurement costs. Secondary pressures also force the issue. Corporations are now required to meet strict internal sustainability targets and comply with aggressive government take-back laws holding them responsible for their waste. This document outlines the formal definition. A closed-loop supply chain integrates forward logistics, the movement from suppliers to customers, with reverse logistics, the movement from customers back to the firm, to systematically recover value from returned products. This chart distinguishes CLSC from the specific components it relies on. While reverse logistics describes the backward movement of goods and recycling manages material recovery, the closed-loop model strategically integrates both directions to maximize profitability. You see this in electronics remanufacturing. Customers return used smartphones, the company refurbishes the internal components, and then resells them as certified pre-owned devices. Heavy manufacturing relies on it as well. In automotive parts remanufacturing, used engine blocks are collected, entirely rebuilt, and returned to the market carrying a brand new warranty. A true CLSC alters a company's relationship with its merchandise long after the sale, treating post-consumer waste as a highly lucrative procurement source. To understand how this functions, look at this baseline architecture. It starts with the highly predictable forward flow of goods, from suppliers, to manufacturing, to distribution, and finally to the customer. The architecture expands when we map the reverse flow. The product moves backward from the customer into an initial collection node. From there, it hits the system's most critical operational bottleneck, the central hub, where the return's physical condition is inspected and sorted. Based on that inspection, the item takes one of 5 branching paths: reused directly, repaired, remanufactured, recycled, or disposed of. The highest value paths feed directly back into the forward stages to officially close the loop. Building this architecture involves integrating reverse material inputs directly into primary production planning, moving the process far beyond the silo of a traditional returns department. Running this dual-flow system on the ground introduces a massive operational headache: return uncertainty. Forward logistics are highly predictable. Operators know exactly what's loaded on a truck. But incoming returns arrive in chaotic, unpredictable quantities at random times. This is compounded by quality unpredictability. You have no idea if a returned item is pristine or completely shattered until a worker opens the box and physically evaluates it. Managing these simultaneous forward and reverse flows requires a level of advanced inventory coordination that linear models lack entirely. You are essentially operating 2 intertwined supply chains simultaneously. Without advanced forecasting, flexible warehouse capacity, and robust information systems, the sheer unpredictability of those returns can easily bankrupt a circular business operation. To ensure the system remains profitable, operators rely on strict principles, starting with value prioritization. This graphic shows the hierarchy of recovery. Direct reuse sits at the top. It holds the absolute highest economic value because it requires the least amount of secondary processing. Below that is remanufacture. Notice the severe drop in value retention when you move down to recycle, because the product must be completely broken down. Contrary to popular environmental messaging, recycling is actually a low-priority recovery method in a closed-loop system. Preserving the product's original assembled form is always more profitable. Executing this hierarchy requires a proactive engineering approach, known as design for recovery. Products must be explicitly engineered at the initial supplier stage for easy disassembly, allowing valuable components to be salvaged intact. Planners have to integrate reverse flow considerations alongside their forward flow design long before the product reaches a storefront. Profitable value recovery is never a happy accident discovered in the returns pile. It has to be engineered into the product's DNA before a single unit is manufactured. We are seeing these principles implemented across diverse sectors, ranging from heavy industrial equipment leasing to consumer fashion resale platforms. The math works aggressively in industries with high intrinsic material value. Battery recycling systems, for example, yield highly lucrative returns by extracting raw lithium and cobalt. It is also mandatory for survival in sectors plagued by high return volumes, specifically e-commerce return management, where millions of items are sent back continuously. But scaling this across industries exposes major systemic challenges. Designing a network that efficiently moves goods in two directions is immensely difficult. As noted in this breakdown of challenges, a critical financial hurdle is cost-to-serve visibility. It is notoriously difficult to calculate the exact cost required to retrieve, transport, and process a single returned item. The macroeconomic potential of a circular system is massive, but the hidden micro-costs of retrieving and sorting individual units can quickly destroy profitability if your tracking visibility is poor. Despite these hurdles, macro trends are pushing global supply chains firmly toward this model, driven heavily by the explosive growth of secondary resale markets. Intense external pressures from ESG mandates are also forcing corporations to systematically redesign their supply chains to prove they are reducing waste. To solve the return uncertainty problem, operators are deploying technological advancements like IoT sensors and blockchain ledgers to accurately track product life cycles digitally. The closed-loop supply chain exists to integrate forward and reverse flows for both strategic and economic advantage. Successful implementation demands intelligent product design that prioritizes value recovery rather than relying on downstream recycling as a crutch. Implementing a closed-loop supply chain creates the logistical foundation required for businesses to transition from linear extraction toward a circular, profitable economic model.